Sure, thanks, Brad. So, and also thank you everyone for joining. Especially, it's great to learn that everyone is like coming from very diverse origins here, very diverse countries, dialing like very different time zones. So, appreciate the time to join. And yeah, a bit about AIDDA Institute. So, maybe for some of you who are not familiar with AIDDA Institute, so we just had a 2-day virtual conference like last month, where actually the first goal that we found AIDA is that we want to make a dedicated community that is focusing on AI-driven discoveries of algorithms and science. Because as you might know, for the past few years, I guess, starting for like the AlphaEvolve work by Google DeepMind, like this kind of line of work of like LLM driven discovery, evolutionary research, which is one of the topics for today's talk, is like becoming more and more popular, becoming more and more relevant in like math, coding, and even science these days. So that's the idea that we want to have a dedicated community. So, and in fact, we held a conference dedicated for that. So if you missed the conference, it's available on our YouTube channel. Maybe later, me or Barrett can link our YouTube so you can catch up with the talks. But after that, now we are thinking about we want to continue and growing this community. So that's why we starting off this kind of like seminar series. And actually, today is the first talk of our seminar series. And again, thank you for Temoor for like accepting the invite to talk and give the first talk for our seminar series. And please stay tuned because we'll have more series of talks after this, and we also have more events. For example, like we will have more hackathons or even like on-site events. So please stay tuned for that. And yeah, maybe if you want to learn more, feel free to just chat me on Barrett, or even later you can also check our website to learn more. And yeah, join our Discord community as well to learn more. So after this, like I just hand it back to Barrett. Thank you so much.
Over to you, Temoor. Thank you for the introduction, Richard. Temoor, if you give a bit of a background, and then, yeah, the stage is yours.
Hi, everyone. Thank you, Richard, and thank you, everyone, for hosting this conference. Yeah, I think you guys are doing great work, and I've been very interested in this direction. So it's great to have, I think, a community that everyone can share things on and present things. I'm Temoor Ali. I'm a graduate from CMU. Recently, I was at Qatar Computing Research Institute. Most of this work is actually independently done. But yeah, I'll get straight into the topic now. I'll be presenting about this paper I worked on, Levi. This is essentially an evolutionary research framework. And the core thesis here is that stronger search architectures can easily substitute for larger LLMs in evolutionary research. I'll start by giving a high-level background, although I think most of you will be familiar with a lot of this stuff. Essentially, when we say evolutionary research, we mean combining, classical genetic algorithms with LLMs as the mutation engine. And these methods are usually involved in discovering new algorithms, new mathematical constructions, heuristics, and in general, different sorts of optimizations. And usually, as you can see from the problems here, they're usually problems that have an easy to verify but hard to search problem. So an NP-hard type of shape for the problem. And they're especially useful for problems where the search space is combinatorially large and it's of a textual form. To motivate, I think, even more of what are the promising results, these are some of the interesting results that we've seen over the last few months within math. I think one of the oldest results, fun search, we had the novel CAPSET construction that we saw, I think, back in 2024, early 2024. And then I think AlphaEvolve built on that, and they discovered, a completely new matrix multiplication algorithms and improvement after I think 50 years or so. I think also a couple 6 months or so ago, Terence Tao got a lot of very nice results using AlphaEvolve. I think 30 plus new constructions in math. Although I think you need some sort of expertise to get at that level. For systems, I mean, again, AlphaEvolve, they optimized Google's Bohr cluster, gaining back, I think, around 1% of their entire infrastructure around the world, which is, a lot for them. And then a lot of, I think, the recent work by the ADRS community has been very solid, and that they've shown promise, I think, across the across the stack, with kernel optimization, with database optimization. And then lastly, I think recently we also saw these kind of methods applied for prompt optimization. For example, JEPA shows that you can actually get a lot of efficiency over by using evolutionary search instead of RL. Despite the interesting results, these kind of frameworks have this cost barrier where even if the impact is clear, making that costs a lot. So a lot of these frameworks, they tend to use oftentimes the strongest and the latest LLMs like Opus or Gemini. And even if they do not use these models, the frameworks are usually designed with these models in mind, right? So even if you try to replace them with smaller models, you'll often see that the results are not as promising. So each run can cost, for example, from $30 up to $100. And if your run fails midway through, that's very problematic. And this raises the barrier to entry a lot. And this is one of the reasons that was difficult for me to start in the beginning. I'm trying to run other frameworks, and the cost barrier is just very high. I think it also limits the set of applicable domains where these kind of methods can be applied. I think when we make sure that the cost is reduced as much as possible, we'll start seeing all sorts of other problems where this can be applied. And I think we'll also move from seeing the results from these frameworks as these one-off algorithmic discovery results that you make a paper out of, to instead see this as a casual result that maybe you can use these frameworks continuously and you apply them in all sorts of problems. And the core of this presentation will be talking about Levi, where I'll show or try to argue that actually you can considerably reduce the search cost and make, at a high level, the algorithmic discovery problem a lot more efficient. And the presentation at a high level will look at 3 different axes. So we'll look at the solution database and how we can invest there to make sure that our database is much more robust to convergence, and why that can save us a lot of cost. And then we'll also look at model routing, where we'll see how to best utilize the model ensemble that we have. And then lastly, we'll look at a proxy benchmark, where for problems where we have a lot of training test cases, we can actually create a proxy data set that is much smaller and can save us in evaluations. And for each one, I'll try to give the intuition or the key insight before it, and then we'll go into the technical details of how it works. For the solution database, I think the first question that comes to mind is, are the strongest models really necessary for evolutionary research? And I would argue actually no, especially the initial results from Front Search, which was one of the starting works around this topic. They actually used a very small model, I think Star Codex or something, that was around 30 billion or so to get their frontier results. And I think another argument for why the strongest models are not necessary is smaller models are getting cheaper and cheaper while only being slightly worse. So you'll find a model that's 20 times cheaper, but only a few points worse in coding. But then why do a lot of the existing solutions and frameworks rely on strongest models? And I think one of the core reasons is that maintaining diversity becomes a lot more difficult when you move to smaller models. Their output space is a lot smaller, and they are very prone to convergence, right? So that's one of the problems we'll try to solve. I think another argument is strongest LLMs actually make a lot of sense when you have a very limited set of evaluations. What I mean by that is, if you're not bound by the amount of dollars you're spending, and instead you're bound by how many evaluations you have. Maybe you have only 30 evaluations or 50 evaluations. In that case, using the frontier models make the most sense, right? They will get you the best results in first 50 iterations or 100 iterations of the search algorithm. But I think that's the wrong trade-off to make, because most of the problems that can be baked with these kind of methods, the evaluations are actually the cheap part, right? You can parallelize them, you can run them, even locally on simple laptops, and they can take, maybe even a few seconds to run. So trying to focus your savings on the evaluations instead of actually the models, or sorry, the models, I think makes a lot less sense. I think evaluations are cheap, and using bigger models is a more expensive part, and that's a trade-off that Levi, I think, tries to make to reduce the cost. To design the solution database, like I mentioned, the high-level requirements are the solution database should be able to fingerprint and distinguish between different algorithmic families. So it should have an inbuilt method to do that. And then at its core, we want the database to start off as diverse and then maintain that diversity through its search process. This is the initialization phase. Essentially, what I do here is we take bootstrapped seeds to initialize diversity. This means we will sequentially generate as diverse of solutions as possible, even if they score low, from completely different algorithmic families, from completely different solutions. And this ensures that even when we're starting, actually we have footholds in all of these different parts of the search space. And we don't actually converge to a single one. Compare that to when you're starting your search space with a single seed, maybe a couple of seeds. It's much more difficult to recover your diversity after you've already let go of it in the beginning. That's why I think it's very important to start off and make sure that the initial set of seeds is extremely diverse. For maintaining the diversity, there's two, I think, main methods that we utilize. We'll first replace the map elites method, which is generally what other methods use, with the CVT Voronoi tessellation-based method. And the main reason for that, it is actually scales very gracefully with the number of dimensions. So with map elites, the issue is that you'll have 2 dimensions. Okay, that'll work fine. Maybe you'll have 100 cells or so if each one of the dimensions has like 10 bins. But the more you try to scale, the more exponentially the number of cells start to increase. And what that'll mean is that a lot of your cells will be sparse, and most of your archive will actually end up being empty instead of being fully utilized. Another thing we try to do is we try to introduce more sophisticated behavioral dimensions to fingerprint these families. So instead of just maybe looking at the runtime and the code length as the 2 different behavioral dimensions, we'll try to look at maybe more of the abstract syntax tree. We'll look at maybe the cyclomatic complexity, the loop count, the peak memory usage. And I think another reason for you choosing CBT map elites is that it offers a lot of flexibility, right? Based on your understanding of the search space, you can actually play around with which dimensions to use, and which ones will actually genuinely represent different algorithm or fingerprint different algorithmic solutions. Even intuitively, for example, you can have codes that are short and long, but actually the logic or reasoning behind it is very much the same. Whereas if you look at a more sophisticated tuple, you can actually try to fingerprint more accurately. This is basically what the solution database looks like at a high level. Like I mentioned, we'll start off by sequentially generating the set of initial seeds that will be the starting point for our archive. We'll also use these to calibrate the bounds of our map elites. What I mean by that is, when I mean cyclomatic complexity, what do I mean? Between what ranges and what is the normalization that we're using? And this initial set of diverse seeds that we created actually helps a lot with that, because we know we're basically using a data-driven method to start off these bounds and initialize the search space and the archive. And the intuition is that hopefully, if this entire initialization process is successful, then we'll have regions that have maybe, a control flow type of family, if we're following along this example, and maybe a different part of the search space will, our archive will maybe focus more on arithmetic families. Once again, we can play around a lot with these dimensions and try to tailor them to whatever problem we're looking at. And they'll also, I think, move beyond just the input type of behavioral dimensions. What I mean by that is a lot of the examples I'm giving here are code related. So what does the code look like? How many loops does it have? How many math operators does it have? In contrast to, for example, looking at how the solution operates in its output space. So if it's a mathematical constructions, what kind of properties does that have? If it's, once again, code, how much memory does it use? How much time does it take? So we can create, a tuple that is a combination of both what our solution looks like and what kind of output it generates. And then the second intuition that, or the second part of the Levi search architecture that I mentioned, and the key intuition behind it is, are all mutations created equal? And this is trivially not true, right? Because some of the mutations will involve, maybe just editing a single parameter. And that cannot be compared with this other change where you're completely rewriting the solution into a completely different algorithmic family. And it would be naive of us to actually dedicate the same amount of compute and the same type of models to each one of those problems. Instead, we need to separate between these normal mutations and these paradigm shifts, these larger jumps in our programs. And we'll rely mostly on smaller models for most of these mutations. So a model like a 30 billion coin is actually great here and works really well for most of the mutations. And we'll use the larger models as creative engines. These will create completely different solutions. They will completely rewrite the solution from scratch. And once again, this is another actually redundant form of diversity maintenance that we're doing here. By continuously trying to generate more and more diverse solutions, we're making sure that our archive, once again, doesn't converge to a single type of solutions. And this is where the larger type of models, I think, or the frontier models can do really well because they have a lot more parameters, they've seen a lot more data, and they can come up with a lot of creative solutions as necessary. To put the picture together, I think this is essentially the part that I mentioned before, where we're initializing it, and then we're calibrating our database with that. And then we'll have these smaller LLMs doing the simpler mutations. And then the larger LLMs will be doing the more of the paradigm shifts. And one of the things that we do is we try to make sure that this paradigm shift that's generated is actually structurally different from all of the existing solutions that we have. And this is where our CVT map elite once again comes in handy because it allows a very clean kind of separation of the search space. So maybe we'll take some solutions that are in this part of the Voronoi tessellations, and then maybe we'll take other solutions that are in this part, and they'll represent completely different solutions with large deltas in their underlying methodology or solution. Yeah, and essentially the loop will run as usual. You sample sample parents, give them to the smaller LLMs, evaluate them, and then score them and put them back. And this loop actually runs in parallel and is asynchronous. So as the LLMs are pulling in, the evaluators are running in parallel to that. And then the last method that I mentioned, where once again I'll try to explain the intuition behind it, which is in a given problem where we have a lot of training examples that are needed to optimize for our scoring function. A good example of this is prompt optimization, where each one of your tasks you'll have a training data set, you'll have maybe 300 prompts or so that you're trying to optimize for. And the key question here is, are all of those examples created equal? And intuitively, it should make sense that actually that's not true. These benchmarks are not meant to create the most diverse and least redundant type of problems. No, instead they'll contain a lot of redundancy, they'll contain a lot of noise, and a lot of the examples will be completely unnecessary. That's one aspect. And then another aspect is that actually we don't even care about getting the perfect score right. All we care about is a data set that gives us an accurate set of ordering between the candidates. So if one solution is more promising than the other, then it should rank higher than the other one. We don't really care necessarily about the exact score that we're getting. And what Levi does is it evaluates on the proxy data subset to preserve that ordering. Once again, this is especially useful from prompt optimization kind of problems. And the way we do the selection is we actually we utilize the bootstrap seeds that I mentioned before, where we will build a simple matrix of the seed solutions that we have, which will be maybe 4 to 5 to 10, and we'll run those on the full data set. So you'll have a matrix with the seed solutions and their scores on each one of the examples, maybe 300 examples or so. And then we'll simply greedily select the examples based on a simple contribution factor, which consists of two main scoring methods. So one will be as simple as rank faithfulness. Does the subset that we're choosing order candidates in the same way as the full set does? And this is just a percentage of the orderings that are accurate as compared to inaccurate. And then we'll also add a separation term where we'll try to make sure that we don't choose the subset of samples that give us the same scores, which will really not bias much. We look more into details on how we choose these parameters and what kind of other methods we experimented with to accurately preserve the ordering. I think that can be found in the paper, but I'll skip over that for now. With that in mind, I'll now go to the experiments where we try to study the contributions of different methods and how well Levi does on different problems. We'll essentially look at two main domains. Each one has different type of cost currency. For code optimization, we'll mainly look at the ADRS systems research tasks. So these are across networking databases, expert placement on mixture of experts. And here the main budget factor is actually dollars. So how much money are we spending on the models, and how expensive are these models? The other domain is prompt optimization, and here we'll use problems taken from the JEPA suite of benchmarks. And here I think the more expensive currency becomes the rollouts. So how many rollouts do we have for each one of the models? And we're trying to minimize those in that case. The baselines that we look at for the code optimization involve JEPA, OpenEvolve, and a lot of the recent methods. And the baselines basically use the frontier models, GPT or Gemini 3.04 Pro, around $15 to $13 per problem. Like I mentioned, it's quite expensive. And then Levi will rely mainly on Qwen 30 billion or the MIMO Lite model for more than 90% of the mutations, and then only use Gemini Flash for paradigm shifts. And even for paradigm shifts, we actually don't use the most expensive models. It turns out even that is not necessary, and instead, a Flash model can do the job really fine. So these are the problems. These are the different frameworks we have. These are the different, like I mentioned, ADRS problems. And as you can see, Levi outperforms all of the benchmarks in all of the baselines on 6 of the 7 problems. And the cost reduction is actually from up to 6.7 times. And on some problems, actually, even though we've spent the full budget, in reality, Levi actually outperforms other baselines at a much cheaper cost. So for example, on LLM SQL, Levi actually reaches a better solution only after using $0.50. Which is, I mean, the intuition that we're trying to go here, right? We don't need to spend $20 when a lot less is enough. And the exception is Prism, which is, I think, a very it becomes very saturated after some time. Almost all of the frameworks, they run into the specific ceiling that they cannot escape. Other than that, we also try to do a more controlled set of experiments. So this essentially means we take specific problems, and then we will compare Levi against other frameworks and try to see how fast each one of the frameworks reaches the desired score. All of the frameworks get the same model, the Qwen 30 billion, 750 evals. We run 3 seats, and the only difference is the harness that we're using. And you can see Levi outperforms the other ones and really reaches some of the top performances very fast. And this is in part because of the bootstrap initialization that we're doing. Even though that step is done mainly to initialize with diverse solutions, a byproduct of that is actually it climbs the initial few points very, very fast. Because you're considering all sorts of these different solutions, it turns out actually that ends up being very good for reaching high scores. Sometimes on some comparisons, actually, Levi has more than 12 times sample efficiency. And then I do a set of ablation experiments where we try to understand how essential each one of the components of Levi is. And here we're comparing 2 main choices. So you have the bootstrap seats, where as I mentioned before, we sequentially generate different solutions. And then we're also looking at the rich diversity dimensions, which means how rich are these dimensions? Are they as simple as, okay, I'll look at the length of the code, I'll look at how long it takes, or will I look at more complicated things like the cyclomatic complexity, the number of math operators, etc. And like I mentioned, the bootstrap seeds actually leads to the biggest improvement. You can see that without them, on both of the problems, actually, the archive quickly converges to a singular family, and it cannot escape that. Whereas if you strato from a more diverse solution, actually escape that very fast. For diversity dimensions, they matter a lot more when, for a given problem, there's a lot of different algorithmic families that are viable as candidates. And it ends up mattering a lot less on problems that have, a singular solution and that are much more exploitation prone as compared to the others. And that's what happens on transactional scheduling here. We'll also try to understand more on what the choice of our models look like. Here, what we do is we have a fixed dollar budget of $50, and we try to compare, Levi, and then we try to compare the case where we don't use any large models, but we still have, rollover routing. And then lastly, we completely remove rollover routing. And very interestingly, actually, for some problems, the best solution is just to not use large models at all and not even try to escape the local minima that you have. And that happens with transaction scheduling, which is a problem that is much more exploitation prone. And it has a single family of solutions that if you really try to exploit on or try to optimize on, that ends up being much better. And in that case, actually using large models in the first place ends up being harmful. And even rollover routing becomes problematic. For other methods like spot scheduling or expert placement, it's a more mixed picture. So Levi actually does much better than the other cases that I mentioned. And removing actually a large model hinders the performance considerably, even more so in EPLB, where actually a small model is really, it's really difficult for it to escape the minima that it's in. Rollover routing still helps, even though it's still the smaller model, but still it cannot reach the better performance that, including the larger model benefits from. And this is consistent with the core thesis where we need to understand which exact type of mutations and which exact type of problems benefit from larger models and which ones are more suited towards, smaller models. We also include, the prompt optimization case. Like I mentioned here, we are taking 4 different problems from the JEPA suite, and then we compare Levi against, the 2 core baselines. And then you can see that at a high level, Levi has a better aggregate score. It improves on some problems. It does competitively on some problems, but it uses, oftentimes less than half of the rollouts of JEPA. And once again, this is mostly due to the proxy benchmarks that we create in the beginning. And this rollout actually includes the amount of budget spent on the initial seed and in the initial proxy creation process. And once again, despite that, we're much better on the rollouts. A conclusion, if there's one takeaway from this presentation, it's that let's try to look at the search harness first and invest there, and not put all of our budget on the largest model possible. And as shown in the previous cases, actually that alone is very promising and yields very promising results. And Levi consists of 3 main components, like I mentioned. Each one tries to optimize for one axis. So a solution database, like I mentioned, its goal is really to try to preserve diversity, rollover routing, like I mentioned, use smaller models for local edits, and use the bigger ones for more rare paradigm shifts. And then lastly, the proxy benchmark, like I mentioned, we want to reduce the redundancy in our training test samples and try to remove any kind of noise that we have. And using these simple tricks, we're actually able to match or even beat frontier baselines at a fraction of the dollar budget or rollout budget. One thing to keep in mind, I think I mentioned this or touched on this at a high level before, which is when we're making this trade-off, we're really trading dollars for evaluations. So Levi, even if it's a lot cheaper, it will use maybe 10 times more evaluations. And that's a perfect trade-off when those evaluations are very cheap. They take only a second. You can spawn tens of those evaluations in parallel. But this kind of solution starts to look a lot less promising, as in moving away from larger models when each of the evaluations is very expensive. So maybe when you're training a model, which may take 30 minutes or 1 hour, using a larger model with the full context and its history will make, I think, a lot more sense because you're much more evaluation constrained in that case. This is at a high level. Thank you, everyone. I'm happy to answer any questions. Feel free to interrupt me. Here's my contact. You can reach out anytime. And here is the GitHub for Levi. I see some questions in the chat. I'll try to look at them.
Awesome. Yeah, maybe I can help read the questions for you.
Yeah.
So yeah, thanks again, Temoor, for the clear and very insightful talk. So we do have some questions coming in. So the first one is from Henry. I guess this question is touched a bit at the end of your presentation, but maybe you can elaborate more. So his question was, in paradigms where evaluations are more expensive, do you expect larger LLMs to dominate the search architecture choice?
Yeah, exactly. Yeah. I think I mentioned that at the end. Exactly. I would say using larger models is much better in those cases. And even you can actually see this trade-off in this ablation, I think, that we had, where it makes a lot more sense for transaction scheduling, but with this other problem, it becomes a lot more difficult.
Okay. Yeah, I think that makes sense. Okay, so maybe we can move on to the next question. So this time is from me. So I want to ask about the initialization phase, right? So did you assume that the LLM can always like produce structurally distinct algorithm families, like when you prompt them to? And so if so, then do you encounter like any situation where all the seeds then eventually collapse into the same family? So in this case, do you just resample, or what did you do to handle this?
So I implicitly assume that the LLM will be able to generate very diverse seeds. And that's one of the reasons why actually this is one of the parts of the search architecture where using larger LLMs is much more helpful. So for initializing the first few seeds, we do use the largest LLM possible, right? I did not really run into a case where it collapsed into the same family. Actually, the opposite. Oftentimes, maintaining all of these different families ends up being harmful for some problems, like I mentioned, where exploitation is a real benefit.
Right.
So you also want to reason through the exploitation versus exploration trade-off on which problems benefit from which one more.
Right, makes sense. I guess it's also depending on like the problem, like it's very problem dependent, like for example, and also like dependent on the capabilities on the LLM, like the knowledge of the problem, right? For example, like if some problem already like well known, they might know like a lot of different algorithms from the literature and they can try all of them. But maybe for like less known problems, then it could be like harder, right? Maybe that's my guess. Yeah. Okay, so another question from Henry. So how does Levi compare to recent hybrid agentic evolutionary search architectures like Coral? Are you familiar with this?
I think I saw it on Twitter, but it was way after I finished working on this project. I was not able to compare with them or include a comparison in the paper, but if I recall, we do outperform them on a number of different problems. But I also think they're trying to go for a different kind of trade-off. I think if they may be focusing a lot more on the evaluation budget instead of,
Right.
for example, cheaper problems. But I've not directly compared with them or seen them. Yeah.
I see. Okay, understood. Okay, we have another question from Harsada. So Levi optimizes programs and prompts today. Could the same framework evolve entire agent systems, planner, retriever, memory, verifier, tool selection policies as the search space?
Definitely, I'm pretty sure it's possible. And I think given that you have different components, you could also use them as your behavioral descriptors. I haven't tried this in practice, but any kind of text can be evolved with Levi. Although you have to be very careful with the evaluation here, right? With an agentic system, oftentimes the evaluation can be somewhat more noisy, I think, which is also a problem you can see in prompt optimization. I think basically, that's it. Hope that made sense.
Okay, yeah, I think that's a good answer, actually. Okay, so I guess if you still have more questions, I guess we'll still have time, so you can still ask your questions. Meanwhile, maybe I'll ask another question. So, can you comment more on like how do you set the weights for the routing like ensemble? Like how did you like alternate or select between the smaller and large LLMs? Do you like adaptively select the weights based on the progress of the search, or do you set it like before you start the problem?
If I remember correctly, I did try making it adaptive. But in my experience, I think assuming, first of all, that first of all, the shift between smaller and larger models is not adaptive at all. It's completely fixed. Every, for example, 10 evals or something will try to go for a paradigm shift. And in my experience, for a number of different problems, that ends up being useful, even if you're moving towards, the later stages. I even tried playing around with the prompt where, as we move towards the later stages, the prompt changes so that the larger LLMs get focused on exploitation more. But honestly, I don't think I saw improvements that were large enough, and I was worried that this will overfit to a specific type of problem.
Right.
But I
I
think
see.
one way of trying to move more and more towards exploitation is playing around with the sampling parameters. So when you have, this large database of 50 solutions or something, how do you sample which solutions based on their scoring? So I use like a softmax to sample from there. And in the beginning, you'll see that we're sampling from very different types of scores. But as the search goes towards the end, it tries to converge and focus more on the highest scoring solutions. So that's one way I think, and it's a tried and tested. I think even Fern Search and Alpha Evolve do this. So this kind of method, I think, is another way to do that.
Right, that makes sense. Yeah, because if I remember correctly, I think like for Shinkai Evolve, they do have like set this kind of like adaptive weights, I think, to the ensemble, right? So they treat this as like as a bandit problem. So like sampling different LMs is like sampling from like different arms, and then based on the reward, like for example, the solution score, I think they then adaptively adjust the weights. And I don't know, but like AIDDA Evolve, I think they also adaptively change that. But I guess your approach is more like you set a schedule, like whenever you think it's time for like paradigm shift, then you just sample from the larger LMs, right? Is that correct?
Yeah. The thing with this kind of adaptive method, or the thing that I was always worried about is, do we have enough evaluations to be able to run that kind of bandit successfully? And I was not able to build the intuition behind that accurately in my head, because assuming we do that kind of an approach where we mix between smaller and large models, it's hard to know if you're overfitting to maybe that local optima. It could be that you start using the largest model one after another, but it has a ceiling and you can't see it within that local landscape. But globally, actually turns out that you kind of shot yourself in the foot by focusing just on that. But honestly, I didn't try it out in detail, and it's a good thing to, I think, reason through.
Yeah, that's cool. Yeah, makes sense. Thank you so much for your answer. So yeah, if the others still have any questions, feel free to type in the chat or even
Thank you.
Bye.
see you next time. Bye bye.
Bye.